Welcome everybody who has joining us online for our third Nature of Change webinar series about Port Phillip Bay, where we explore the changes over time of the bay's incredible ecosystems and the people who live there. After a cracking two first webinars exploring the history of the bay and looking a bit in a bit more detail in terms of marine ecosystems and water quality, tonight's focus is on the science that underpins climate change and the dynamics that shape our coastal landscapes, as well as the coastal hazards that are faced in Port Phillip Bay and the impacts of those. So we've got two incredible speakers tonight, which we're going to introduce very shortly. So tonight is a collaboration between Lifesaving Victoria, the Association of Bayside Municipalities, and the Victorian National Parks Association. So I'm Shannon, if I didn't introduce that, and we've got Hayley and Paul online as well, who you'll be hearing from them very shortly. So firstly, we'd like to recognise the different parts of Port Phillip Bay as sea country for the Bunurong and Boonwurrung people on the eastern and northern side, and the Wadawurrung peoples on the western side. And there's such a rich cultural history, throughout the bay and around its shores that has been alive for thousands of years. So we acknowledge the elders past, present and future, and thank all traditional custodians for taking care of Port Phillip Bay over thousands of years and for giving us the inspiration for how we too can live, work and play, with a lot lighter impact. So without further ado, I'll pass it over to Paul in a second to introduce our two incredible speakers. But just before I do, a quick reminder that we've got two speakers this evening, and please feel free to ask questions throughout the webinar. At the bottom of the screen, you'll see a button called Q&A. So hit that button, post any questions that you have for either of our speaker, and if you can please address the name of the speaker, either James or Jack, who you'd like to answer your question, that would be very helpful for us. And we will aim to finish by 7 o'clock. And this webinar will be recorded and sent around afterwards for you to rewatch. So Paul, I'll hand it over to you to introduce our speakers. Oh, and we can't hear you.
Sorry, I was just wishing you happy Valentine's Day. Not. Lifesaving Victoria is thrilled to be part of this program, and today to be able to welcome a feature presentation by Dr. James Driscoll is really fantastic. With a keen focus on the profound impacts of climate change on our beloved coastal communities, Dr. Driscoll brings a wealth of expertise and insight to the discussion. In 2012, James ventured into academia at Monash University, where he now serves as Director of STEM Outreach, passionately driving scientific literacy initiatives. At the Faculty of Science, he champions outreach programs focusing on earth sciences and climate science. Drawing from his extensive background in geological exploration and academic research, Dr. Driscoll will delve into the intricate ways in which climate change is reshaping our coastal landscapes. Join us as we delve into the critical topic and discover the pathways to safeguarding our coastal environments for generations to come. Over to you, James.
Thank you so much for that. And if I just also reiterate that how important is the Indigenous knowledge that we have. Certainly myself and many of my colleagues see Indigenous peoples as being our first scientists, our first astronomers, our first geographers, and the information that we can get from their oral traditions and oral encoding of science is just awesome. So just wanted to reiterate that. Okay, so let me just make sure I get this right. Okay, so you can work. That's it. Excellent. All right, I'll just minimize that as well. Perfect. Okay, so welcome everyone. I thought that we'd start off today with my half presentation, really looking at how we know the climate is actually changing. So we're going to be looking at the science of climate change. And giving you data and some perspectives on what's happening, how we know it, and what the future may hold based on modelling by scientists. And I thought I'd just give a little bit of signposting. We're going to look at the greenhouse effect first of all. We're going to look at how we can measure the CO2 levels in the atmosphere and actually see how they're changing as well. And we're also going to look at the empirical evidence which shows that we are actually driving climate change. We can look at proxy data so that we can go back in time and look at the paleoclimatic record and see how climate has changed in the past. We're going to do a little bit on the difference between weather and climate, and you'll see why that is important when we get there. Then I quickly swing by Melbourne for some comparisons and contrasting data on climate. And finally, we're going to really look at, why do we care? Looking just at rising sea levels, which will feed into Jack's presentation, and looking at more global scale about biome disturbances because of the climate's vagaries that we see at the moment. I thought I'd just quickly start with this as an engager. It's a really, really good site. It's called Show Your Stripes. I've just opened it up on my computer. So let's just have a quick look at it. And it's really a nice way of actually demonstrating how temperatures are changing in various parts of the world and cities. I've opened up Australia here, and we can easily put in Melbourne just here. And it really kind of gives us an idea of a graphical representation of the hottest through to the coolest years we've had. This is from 1856, and as we'll see in some work which I'll show you shortly, in Australia we really start temperature data from 1910 because that's when we start getting reliable records where we're all looking at the same thing. So it's a nice little thing for you to look at, Show Your Stripes. Yeah, so I'll show you that. All right. Good. So first of all, let's look at the greenhouse effect. And one thing I just wanted to point out is this term called albedo. Now, albedo is a little bit like if I go to outside yesterday when it's a rather warm day throughout much of Victoria. If I put my hand on a black car and put my hand on a white car, you would find that the black car feels hotter to touch than the white car. And that's because black cars have very, very low albedo, and white cars have very, very high albedo. And albedo is literally just how much light that hits the surface is reflected without being absorbed. And we can. The important thing about that is because when we have visible light coming in from the sun, things like clouds can actually reflect some of that incoming solar radiation. So when I use that term albedo, that's what it's looking at. How much light hits the surface is reflected without being absorbed. So with the greenhouse effects, nice, easy 5 steps here. First of all, we have visible light, solar radiation coming in from the sun. We refer to that as shortwave radiation. It can either be reflected by the Earth's Earth or clouds in the atmosphere. That's that term albedo. So if we've got ice caps, for instance, or glaciers, and we have visible light actually hitting those, much of that will be reflected back into space. However, if we've got the Earth itself or water, that's a darker color, and so that means that the light will actually be absorbed, that radiation will be absorbed. So about 50% of that is actually, of this incoming solar radiation is absorbed by the Earth's surface. That's land and the oceans. It's re-radiated back from the Earth's surface as long-wave radiation or infrared radiation, and that is why we have the greenhouse effect, because in the greenhouse effects in the troposphere, we have gases such as carbon dioxide, water vapor, and methane, which basically start to trap some of that re-emitted heat as long-wave radiation. Now, it's really important to note that greenhouse gases don't absorb incoming solar radiation. It's the reflected or re-radiated energy from the Earth's surface, that infrared radiation, which is absorbed by the greenhouse gases, and that's what keeps our world warmer than what it should be. So that's just a quick outline of what the greenhouse effect is. Some of these greenhouse gases, I've kind of put up here the atmospheric composition of the Earth's atmosphere. And just up here, you'll see that we have oxygen, nitrogen, and argon are the 3 main gases. Nitrogen is by far the greatest composition of the atmosphere. But then you can say a little word there, trace. So basically, there's trace amounts of gases in the atmosphere, of which carbon dioxide is the most prevalent. And you can see here, 423 parts per million of the Earth's atmosphere is currently carbon dioxide. And we can look at how that changes through time shortly. So there's 3 very important greenhouse gases. We've got carbon dioxide and methane. And the other one, which is really important, but you don't hear much about because it's already, it's not one of those ones which is hugely being emitted by human sources, is water. So water is actually a greenhouse gas as well. Now, you're probably wondering, oh yeah, the Earth is 4.6 billion years. Just thought I'd throw that in, just so you know how long the atmosphere has actually been on Earth. Now, you're probably wondering, why don't we include water vapor actually within the atmospheric composition? And the reason we do that is because the amount of water vapor in the atmosphere is very variable. And you can see here that depending over the tropics, there's much more humidity and much more water vapor, whereas at the poles, we get much less humidity. And that's a function of the temperature of the atmosphere. The warmer the atmosphere gets, the more water vapor it can hold. And it's usually is about 1 degree Celsius rise in temperature. It means you get 7% more water being held in the atmosphere. And we'll get to that shortly, why that's a really important consideration for us. So we have 3 dominant sources of greenhouse gases that come from natural sources. The first one, we've got a lovely shot there, Mount Pinatubo in the Philippines in 1991. So we have volcanoes. Volcanoes actually emit a lot of greenhouse gases. Okay. Swamps and decaying matter, that's another one of these dominant sources of natural greenhouse gases. And the third one is bushfires. So wildfires or bushfires, depending on where you live in the world. These are the 3 dominant natural sources. I just want to point out these are natural sources, and the Earth's atmosphere has been in sync with these sources for hundreds of millions, if not billions of years. So there's a natural order of how much greenhouse gases are in the atmosphere over a long period of geological time. Yes, they go up and down, and we'll see why that is on natural causes shortly. But I just wanted to point out these are 3 really important dominant sources of greenhouse gases in our natural world. This is one thing I always show students. So with the greenhouse effect, the average surface temperature on Earth is 15 degrees Celsius. If we didn't have the greenhouse effect here on Earth, it would be minus 18 degrees Celsius. And that's pretty stunning. That's a 33 degrees Celsius change in the temperature on Earth based on literally trace gases within our atmosphere. So small changes in the greenhouse concentrations in the Earth do lead to big effects within the temperature which is being experienced on Earth. Okay? So the greenhouse effect is a good thing for Earth. What is a bad thing for Earth is the fact that we are pumping excess CO2 into the atmosphere, and that is what is causing the current climate change here on Earth. So let's look at the 4 dominant anthropogenic or human sources of greenhouse gases. First one, burning fossil fuels. Okay, so basically you're taking coal, or you're taking gas, or you're taking oil, and you are burning it, and you are releasing carbon dioxide and other greenhouse gases into the atmosphere. Next one is deforestation. By cutting down trees, you are basically having an effect on the amount of CO2 that can be stored within carbon within these forests. If you cut them down, they're just going to decompose and just add CO2 into the atmosphere. Third one, of course, is cars and transportation. That adds a huge amount of CO2 into the atmosphere by burning fossil fuels, and that's why EVs are becoming so popular around the world. Of course, we have to be mindful where we're getting the electricity from if EVs are going to be a nice, clean energy, because, of course, if you're taking that energy, which is powering EVs from burning fossil fuels, it's probably not such a good thing. It'll be best from hydro or solar. And the final thing, of course, is agriculture. And here we have some lovely cows, and when cows burp quite a lot, they release methane, and methane is a particularly potent greenhouse gas. So there are 4 dominant human sources. And I've just included some work here from NASA. It is a fact, and this is some climate skeptics say this is incorrect. It's not incorrect. It is a clearly demonstrated fact here that there is a strong relationship between increasing atmospheric CO2 concentrations and the surface temperature we have on Earth. We will talk about these ice cores shortly. Anything from about 1958, all of these is directly measured data of CO2 in the atmosphere. Anything before 1958, we actually have to look at ice cores for that. And we'll discuss that shortly. Notice that the 14 hottest years have been since 2005. So with increasing CO2, we get increasing temperatures. And this is from NASA work and UK BOM equivalent as well. Okay. Just wanted to put on this year. This is 2023. All of that data there is from 2022, and I've just added this last little thing here I was over in Europe earlier, in the middle of last year, in Italy, Greece during the heat wave, and it was quite phenomenal just how bad it was over in Europe. They haven't published results yet, but the previous large heat waves they had tens of thousands of people dying because of the heat wave and stress-related diseases, illnesses. Sorry. 2023 was approximately 1.36 degrees Celsius above the pre-industrial mean. So we really are causing some serious issues here with the amount of temperatures we're getting on Earth from human climate change. So let's look at CO2 and how do we measure it? We've spoken quite a lot about CO2. Well, we measure it from two main points that are usually referred to in the press. One is over here in Hawaii, that little red dot. One is down here in the Antarctica, which is Vostok, or South Pole is another one that's used. Now, those 2 points there are really important because, as you can see, they are far from industrial sources. That they're testing really the cleanest air on Earth, basically, are being tested at these two sites, one in the northern hemisphere and one in the southern hemisphere. The reason we try and use the pristine air is because that gives us a really good idea of the average CO2 in the atmosphere. If you're close to industrial sources, you tend to get quite high readings of CO2 because you're burning fuel nearby. So on Hawaii, this is where we are, big island. It's pretty funky, been there quite a lot of times doing field works, great place. And we measure the concentrations from the top of Mauna Loa, which is about 4,400 meters above sea level. Unfortunately, back in 2022, Mauna Loa erupted. And so they had to change to a site at Mauna Kea, which is close by, but it meant that the trade winds are normally coming from the northeast here, which basically meant that any CO2 being emitted by the volcano wasn't being recorded by the pristine air, and so therefore there was no errors associated. So for several months, that's where we did CO2 measurements. Now that Mauna Loa is erupting, we've gone back to from Mauna Kea to Mauna Loa. So let's look at the record. This is the record we have for Mauna Loa. CO2 parts per million on this side. When they started doing this work, we were around about 316 parts per million. Now, up until 2024 to January, we're up to 423 parts per million. So you can actually see that we have been increasing substantially over the last 70 odd years. Why do we get a sawtooth pattern? It's a really good question. We get a sawtooth pattern because of photosynthesis. And in the northern hemisphere, where Mauna Loa is, we tend to get a lot more forests because we have more land in the northern hemisphere compared to the southern hemisphere. And that basically means that during spring and summer, the plants and forests are basically taking in CO2 because they're basically growing their leaves and fruit, etc. And then during the autumn and winter, they're shedding their leaves. They're going almost into hibernation over winter, and so they're not sucking in CO2 anymore. And so that's when we get our peaks during the winter months in the northern hemisphere. So that's why we end up with those peaks and troughs going through. They're quite cyclical, as you can see, because obviously in the northern hemisphere we have spring, summer, autumn, winter are quite cyclical. So that's why. You can get information here from that website. In January 2024, we were at 422.8 parts per million. If you go back to January 2023, we're at 419.5. If you go back to January 2022, we're at 418.1. Now, it's the last couple of years, instead of going up by about 1.5 to 2 parts per million, we're seeing an acceleration in the amount of CO2 going to the atmosphere and being recorded at Mauna Loa. And that is quite worrying because we are trying to, we've got all of these policies to go to net zero by 2050. Will that be enough? That's a big question, which at the moment lots of scientists are working on. So it's quite concerning that we're getting quite a large uptick now in the amount of CO2 going in measured at Mauna Loa. And just to reiterate, without the greenhouse effect, we would be a frozen wasteland. And the concentrations of CO2 over the last 800,000 years before the Industrial Revolution were somewhere between 185 and 275 parts per million. So as you can see, we've more than doubled the lower part of that. And we're approaching about 40% of the upper part of that. Okay. All right, I'm going to play this. This is actually quite a nice video. Oh, actually, before I play it, let me just explain a few things. First of all, you can see there's a map of the world just up here. Okay, this is showing all of the different CO2 monitoring places through time. This is 1979, and we're kind of like in October, November. Okay, this line here at the bottom, this is showing lines of longitude, no, latitude even, latitude. 90 degrees south is the South Pole, which is this blue dot here, this is the blue dot here. 23 degrees north is Hawaii, which is here, that red dot. And you can see there's a few other spots here which are measuring CO2 measurements. Probably the most important one for us that will crop up is in Tasmania at Cape Grim. Cape Grim's been recording since the 1970s, and that's probably one of the ones which is showing just down there. Okay. So let's see how things change through time. So as you can see, red seems to be the Mauna Loa readings in red there. They seem to have much more of a sawtooth pattern. And as I said, that makes sense because in the Northern Hemisphere, we have great expanses of forests. And so they're seeing that real big sawtooth pattern as a result of that. In the Southern Hemisphere, we don't have as many forests, so we're not quite seeing that same. It's much more subdued, that seasonality in the CO2 measurements there. As we go through time, in the late 80s and the 1990s, you can see a lot more places are coming online to measure CO2 in various countries and cities. You'll start noticing there's some big swings about 50, 60 degrees north, and that's because there's quite a few spots now which are opening up in Europe, North America, and East Asia, and they are near major pollution areas, and that's why we're getting those big swings in CO2 being measured. But you'll notice that the blue and the red really are what we tend to think of as the two main places where we're measuring all this information. So that's why that's so important for us to consider those rather than all the other CO2 measurement stations in the world. This goes up to, I think, 2021. But you can see the CO2 levels are increasing considerably, even in this short period from 1979 there. When we go back from 1979, we're actually using data from Hawaii to go back to 1958. So Hawaii, there we go, 1958, the maximum in March 1958, it was 316 parts per million measured. So since 1958, you can see just how these CO2 concentrations have been rising through time. Okay, so that's basically how we measure CO2. It's all empirical data, which means it's directly measured from the atmosphere. And this is just really just to show you the idea of forestry cover in the Northern Hemisphere compared to the South, which is why we don't have that sawtooth pattern in the CO2 concentrations. So how do we go back in time? I mean, we can't do share, we can't sing, you know, if I can turn back time, don't have a TARDIS like Doctor Who. So we need to use something called proxy data. And what proxy data means is that we are looking at data derived from a secondary source in order to tell us what the atmospheric compositions were back in time. And we can use ice cores. Ice cores are a really good way of doing this. So when we have snow falling in Antarctica or Greenland or in the Arctic, basically as that snow falls, you get little bits of the atmosphere being trapped between the snowflakes. And through time, more and more snow falls, which means that the lowest layers of the snow start gradually turning into ice. And as it turns into ice, that's where you're getting the CO2 and other atmospheric gases being trapped. Then what we can do is drill ice cores, go down hundreds or even thousands of meters, take that ice core out, and then we can start measuring how much greenhouse gases are in the atmosphere. So it's called proxy data. It's a really, really good way of us being able to see what's happened over the last 700, 800,000 years. And this is what that ice core looks like. You see just here, they do work down at EDFL, CSIRO, where they actually look at the atmospheric gases from ice cores which are collected. And two of the main places have been Vostok and the Law Dome, which is within the Australian Antarctic Division. So that's two places where we can actually go down thousands of meters and go back hundreds of thousands of years to tell us what the atmospheric gas composition was through time. And that's what it looks like. It's almost like a little speckled just there. Speckled, all of those little speckles are basically atmospheric gases which are trapped in the ice. And this is what 42 years of ice core kind of looks like. It's almost like a barcode. So during the summer, when there's a little bit of melt, it basically means that any dust or material which is settled on the ice starts to end up being darker stripes, and the lighter stripes are during winter when there's more snowfall occurring. So it's about 42 years worth there, and that's from a Greenland ice core taken in the 1970s. So let's go back in time. Let's watch our video. So we're going back in time now. All of the information you're going to see now is from ice cores. And as you can see, this is why it's so concerning with what's happening at the moment, because we have this huge peak up here where we are at the moment. If we go back in time, we can go back about, I think this goes back about 800,000 years. You can see that, yes, we get more CO2 and less CO2 in the atmosphere. That's a function of the ice ages and interglacial times on Earth. But over the last 800,000 years, we haven't seen anything like this. You're wondering why we get ice ages and interglacial periods. It's all to do with something called Milankovitch cycles. So have a look at that online if you want to know more about that. And at the end of this video, this just shows you all of the people who are working to collect this data, many universities and government agencies around the world. All right, so what we're doing, I want to look now between the difference between weather and climate. And the reason why this is important is because of a lot of climate change deniers try to murky the waters with this a poor understanding of this definition. So weather is basically what is recorded each day. So yesterday it's really, really hot in Melbourne. Today it's been pretty cool. And there's some good sites you can go to. For instance, Noel School Earth is a really good website you can go to look at real-time weather data around the world. Have a look at that if you're interested. It's really cool. And this is just giving you an idea that, you know, on this particular day in the morning, it was quite nice in Melbourne. And then in the afternoon, we had a cold front going through and we probably ended up with cloud and rain. So weather changes by minutes, by hours, by days. That's what we mean by weather. And just to give you an example here, I've chosen the January 2024 data from BOM. As you can see, on the first day of January, it was 23 degrees and it was 24 degrees on the second day. So all of these things to do with temperature, precipitation, cloud cover, the amount of sunshine, wind strength, wind direction, these are all components of weather over short periods of time. But what we mean by climate is what's happening over longer periods of time. This could be months or decades or millennia. And so what I've done here is I've actually got the information here for from the BOM here for January 2024 at Olympic Park in Melbourne. And you can see you've got the highs and lows there, but the mean temperature, maximum and minimum, is recorded there as well. And that's what we mean by climate. It's what's happening over longer periods of time. And a nice way of thinking about it is that climate is kind of like the sum of long periods of weather. Okay, it's what you would expect on average at a particular location at a particular time. So we can get climatic results here, which is basically showing us the daily maximum temperature in July. We can look at rainfall as well, and this tells us what the average annual rainfall is in Australia at different areas. This is what we mean by climate. And I just want to show you how we get that information. Oh, sorry, first of all, this is why we care about the difference between weather and climate. You know, Donald Trump, some of his wonderful tweets goes on and on about this idea that it's really cold, so therefore, you know, we don't need to worry about global warming, as he says, or climate change. So this is why a distinction, knowing difference between weather and climate is really important. So let's look at the temperature chart. And again, I've chosen Melbourne here, and I've chosen 5 years of the maximum temperature recorded in Olympic Park between 2016 and 2020 in March. And if we look at the 1st of March, over those 5 years, ranged from about 38 degrees in 2019 all the way down to about 21 degrees in 2017. Okay, so on that one day, we can see quite a large range in temperature differences here in Melbourne. I'm now just going to plot all that information on. It's very pretty. We should speed up. And there we have it. So this is the temperature recorded in Melbourne, maximum temperature per day. And from the 1st until the 31st of March, you can kind of see that there's a general trend of warmer temperatures to cooler temperatures. And that makes sense because we are going from summer into autumn. So there's a very general trend, but it looks like a dog's breakfast. It's all over the place. So what we need to do is we need to think about how we can actually visualize that data and get a definitive value for what the temperature should be roughly in Melbourne during that 5-year period in March. 156 data points, and we have the highest and lowest recorded there. Again, big disparity between the two. So what we can do is we can plot a histogram. And a histogram is really a graphical representation of all that data and putting it into 1 degree bins, we call them 1 degree bins or 1 degree groupings. So if we do that, we start to get a better understanding of what we're looking at the data. Again, it's not a perfect distribution. It seems to be warmer, kind of like around about here. But again, we need an actual value so we can compare different years and get an idea of what's happening to the climate. So what we can do some funky stuff. We've got a nice range of variation in the atmosphere. And if I start doing standard deviation to calculate the mean temperature for all of those 155 pieces of data, this is what we end up with. We end up with between 2016 and 2020, in March, the average temperature is 24.9 degrees Celsius. Now you may be wondering, so what? Well, I'll show you why this is important. Because the average daily maximum temperature in March has been calculated for Melbourne. And if you look at the data between 1961 and 1990, which is the baseline 30-year period that we use, so instead of using 5 years for March, if we take all of that information between 1961 and 1990, the average temperature in Melbourne is actually 23.9 degrees. So it's actually increased by about one degree Celsius in March in Melbourne during that 5-year period. Okay, so that is how we can actually start to show that the temperature is increasing. All right. And this is a nice view, really, just to show that as well. This is just another way of showing it. And this is actually for the whole of Australia. The reason we choose 1961 to 1990 to calibrate what the mean temperature is over a certain period in Australia is because that's what the World Meteorological Organization suggests. Usually 1951 to 1970 or 1961 to 1990, 1951 to 1980, sorry, a 30-year period. And if we do that for the whole of Australia, what we can actually do is we can get a nice average doing that standard deviation, and we end up with that value of 21.8 degrees Celsius, which is the average temperature in Australia. We can then start looking at what the patterns are, and I think you can see there's a clear increase in the mean temperature in Australia since 1910 when we have reliable records. Okay? This is the data which shows how the temperature is changing. All right. We are getting an increased frequency of extreme heat days as well. You can see from this chart, it's quite obvious. A lot of this data is actually derived from neurometeorology. I am very aware of the time, so I'm just going to flip just a bit quickly here. We can do the same thing with rainfall. Exactly the same thing with rainfall. When we look at rainfall, we can see that the average rainfall in Australia since 1900, between 1961 and 1990, is 465.2 mils of rain. Again, we can start comparing and contrasting all of that different annual data, and we end up with plots which kind of look like this. This is actually showing that anomaly. Is it cooler? Sorry, is it wetter or drier than that 1961 to 1990 period? I think you can probably see that since the 1970s, we're starting to get more extreme weather events, whether it be extreme rainfall or extreme droughts. This period here is showing greater variability compared to what we had before 1970. So this is why we seem to be getting more severe weather events here in Australia. I've just done a SWOT sort of like analysis here to show all that data. If I combine the weather, the temperature and the rainfall data, you can actually see anything which is above the line here means that it's wetter than average. Anything below this line is drier than average. Anything to the left of this line means it's cooler than average, and anything to the right of this line here, it's warmer than average. I just wanted to show you this. You can see that the red dots from 2010 to 2023 seem to be much more over this side. We actually run through those 20-year periods. So this is the first 1910 to 1929, 1930s, 1949, 1950s, 1969. And as you can see, as we go through those 20-year periods, you can actually see quite clearly that it's becoming more erratic, the rainfall, but it's certainly getting warmer compared to the previous years. Okay. All right. Final thing. Why do we care? We know there's natural variability in climate. We know that sometimes we have hot years, sometimes we have cool years. That's why the longer the climate record is, the better for us to actually be looking at how the climate is changing. In Australia, temperature we've used from 1910 for temperature, and for rainfall we've used since 1900. We've used data science, showed you data science to show that CO2 levels are increasing rapidly, and for us to calculate the how we derive temperature and rainfall charts. And we can see there's a clear relationship between increasing CO2 levels and temperature. But ultimately, why do we care? Well, from a global perspective, the Earth is divided into a number of biomes. These are terrestrial biomes, so we have things like tundra, which is frozen areas, not wasteland, frozen areas. We can have forests, we can have deserts, or that kind of thing. All right. These are all based on temperature and rainfall. Okay. If you have high temperatures and high rainfall, you basically get tropical rainforest. If you get low precipitation and low temperatures, you end up with tundra. What's important here, though, the boundaries between all of these terrestrial biomes are constantly in flux. They are not static, because as the climate changes, so do these boundaries. The boundaries don't change, but the actual biomes change in specific locations. And what I mean by there is, if I've got a place if I've got a tundra environment which is at -1 degree Celsius, if I have a 2 degree Celsius increase in temperature, that's going to start pushing it into a forest biome, which doesn't sound too bad because it's just changing the biomes or ecosystems. So what's the problem with that? Well, there is a big problem, and that is a lot of CO2 and methane is actually trapped within the ice in tundra systems. If we start melting the tundra and the ice, that methane, CO2, and greenhouse gases go into the atmosphere, and we end up with something called a positive feedback loop. And that's just what I mean by that. Now, it doesn't really matter. In the deserts, we increase the temperature by 1 degree or 2 degrees in the desert. It's not really going to change that biome, but it certainly does in some of these more high latitude areas. And NASA have actually done quite a lot of work on this. They reckon by 2100, about 40% of terrestrial biomes will change from one ecological community into another. And as you can see, when we're up in the higher latitudes, that's where the major changes are going to go. So just to lead into Jack's presentation, we can see sea level rise. If you look at sea level rise, we can see that since 1880, it's increased by about 240 millimeters. You start looking at global sea level rise, it was increasing by about 1.4 millimeters per year in the 20th century. Now it's increasing by over 3 millimeters per year. And that's a function of thermal expansion of seawater, melting of glaciers, and melting of the ice caps in both Antarctica and Greenland. Before 1993, we were using mainly tide gauges, and since 1993, we're using satellite data. So we're quite happy with the data sets we've got. We can actually go back to 1880 with this data set. So I'll leave that. I hope that gives you some context of why we know the climate's changing and what the drivers are. What we're going to do now is I'm going to stop sharing, and I think we can go through to Jack to continue this.
Yeah, thanks very much, James. Very comprehensive coverage, and for someone like me with my level of knowledge, it's absolutely provided some great clarity. And as you say, good lead in to Jack. Now, Jack's a distinguished coastal processes scientist with a robust research portfolio spanning coastal hazards, rip currents, erosion, and sea level rise. Jack brings invaluable expertise to our discussion. Through a blend of coastal observations and numerical modelling, Jack unravels the complexities of coastal change and sediment budgets. Since joining the Victorian Department of Energy, Environment and Climate Change in 2020 to lead the Victorian Coastal Monitoring Program, Jack has authored over 40 peer-reviewed articles, solidifying his status as a leading authority in coastal science. Join us now as we delve into his insights and explore strategies to mitigate coastal risks in Port Phillip Bay. Thank you, Jack.
Thanks for that, and thanks, James. That was great. That talk. It's really interesting. There's a bunch of things that updated me that I wasn't aware of. All right, I'll just jump in. Yeah, I was going to talk about, get down to the nitty-gritty of talking about coastal change within Port Phillip Bay. I mentioned I'm with the Victorian Coastal Monitoring Program in DECA. So I wanted to acknowledge the other members of my team and the academic partners that we work with. Also wanted to acknowledge and pay respect to the Victorian traditional owners. That's the Wurundjeri, the land that I'm on today, and also acknowledge up where I normally am in New South Wales, the Awabakal. All right, this is a really nice video from some of the drone work that we do that was put together by Beck Stewart and Blake Allen in the VCMP team, and that'll do a better job than I could at introducing what the VCMP is all about.
The Victorian Coastal Monitoring Program was established in 2017 to increase our knowledge of coastal processes, assist with evidence-based decision-making, and ensure we have resilient coasts in the future. Gathers data using a variety of methods, including drone surveys, wave buoys, seafloor mapping, sediment sampling, and much more. The data is publicly available through a number of portals, including CoastGear and Vic Waves. Our projects would not be possible without the work of citizen scientists. If you would like further information or to get involved, please contact us.
Thanks, Beck. That's on our website, that video, and Beck also put together this cartoon graphic that explains what we do. And so I won't talk too much about the VCMP today, but yes, we collect data, research and development, develop decision support tools and knowledge management products. One thing that I've been involved with quite a lot over recent years is the Port Phillip Bay Coastal Hazard Assessment as an internal expert advisor. So this talk's going to be informed by the public recent release of that report and the various data, as well as my background in coastal processes. So what we'll do is go through like a 101 of drivers of coastal change over sort of 1 day up to 100 years. That's management engineering time frame. Talk about it in the context of the Port Phillip Bay Coastal Hazard Assessment. That's quite topical at the moment, but I won't go into that one too much because there's a number of workshops and other things going on with that assessment, and the last one of those is on tomorrow if you wanted to attend. Then get into some of the tricky areas around why projecting future changes to the coastline is quite complex with high uncertainty, and some of the myths around coastal change. And then finally, try and give a bit of advice that hopefully incorporates some of my perspective into coastal management planning. All right, so we start with this word equation for describing coastal change, and the processes there are in the cross-shore, along-shore, sources and sinks, and sea level rise recession. And we'll go through what each of those mean in detail now. That's Sandringham. You'll notice there's a lot of examples using Sandringham. Those two groins there you might be aware of. We'll cartoonify those and then start to step through the processes. So if you're looking down from above, if we're looking at the beach there, if we have a big storm that comes in, it'll take sand offshore and put it in a shallow subtidal in a nearshore bar, and this is cross-shore transport. So the on and off the beach, that's in the cross-shore. Next one is in the alongshore. If we've got waves coming in at an angle, so this black arrow here is indicating the wave direction, coming in at an angle to the shoreline and push sand along the shore, and then the waves switch direction and push sand in the other direction. More on that and why that's important in Port Phillip Bay shortly. Other sources and sinks. So this might include estuarine exchange in Port Phillip Bay. Beach nourishment is quite important. So this is indicating you're just adding extra sand to the system through beach nourishment. And then the big one at the end, the big question around sea level rise and erosion or recession associated with sea level rise. And the simple picture on what is expected to happen with sea level rise is that as you raise the sea level, if this is looking in cross-section, the profile will raise up and onshore. And more detail on that shortly too. Okay, now One other thing to point out here is that shoreline change through a few equations, won't go into, you can convert it into sediment budget, which is all the sediment coming in and out of the system on different timescales. And so I might interchangeably use those two terms, shoreline change or sediment budget. One can be converted into the other. So we'll step through those processes again, the coastal change processes, but this time we'll look at the timescales over which they operate. So another cartoon here for in the cross shore, for this storm demand, it operates over a short time frame. We generally think of a few days to years at most. And again, if we have a normal beach to start with, the storm comes in, large waves take sand offshore, and then generally what happens is with more moderate waves over the ensuing days, weeks, and maybe months, the sand is brought back on shore. On to the next process. This is now the longshore drift. Again, if you've got waves coming in at an angle to the shoreline, you'll move sediment along shore. This is longshore drift, and this operates generally the consequences are seen at a longer time scale, over seasons to decades. And the first myth that we'll bring up, this is one that you commonly hear. The myth is that most long-term beach erosion is caused by storms. That's a myth. The reality is that in most cases, storm erosion is cyclical. You see a big storm come in, erodes, and then you see recovery over time. In cases of long-term serious erosion, it's more likely to be issues around longshore drift that are causing that erosion to become severe over time. All right, a couple of examples in Port Phillip Bay, beach rotation, we call it. It's an longshore process at Sandringham. So we saw this in cartoon earlier. Now we've got some real data from Dave Kennedy at Melbourne University, some work he's done. So in the summer, waves coming from the southwest, pushing sediment towards the north. The blue areas you see here build up against the groins. And then in the winter, the waves change direction, and you see now the blue building up at the south end of the beach and erosion south of those groins. So this is really quite important for beach width at certain sites along Port Phillip Bay. At this particular site, you see just seasonally up to 30 metres of change in beach width in some of those areas near the groins or near the headlands. So quite an important process, beach rotation, for that one in Port Phillip Bay. All right, Paul, could you give me a nod if you can see the animation here? Yep, great. So these are some GIFs produced from satellite imagery from Google Earth Engine. And these are some of the most dynamic areas around Port Phillip Bay. So this is, we've got about 30 plus years of satellite imagery here. And so this is called spit formation. Sometimes it's called flying spits. One here on the left is at Swan Island. You can see rapid extension of that sand spit over the course of several decades, and not quite as impressive because the waves aren't as big up there at Altona, but there is still quite a rapid growth of that spit moving up towards Altona Beach. And you see these areas are quite distinct in the Port Phillip Bay Coastal Hazard Assessment because there's very high uncertainty around them. Onto the third process, the sources and sinks and the timescales at which they can operate over. This is quite variable because it covers a range of processes. So it might be estuarine exchange. What that means is sand going in and out of estuaries, and Port Phillip Bay itself is a very large estuary with a number of smaller ones that come off it. But we're going to focus more on beach nourishment, and this can operate over variable timescales. So with our example here from Sandringham is again from Dave Kennedy's work, and this is quite recent. This was 2-3 years ago. This nourishment was occurring, and you see the volumes here that we're dealing with generally in Port Phillip Bay and Victoria in general. That number on the order of magnitude of about 10,000 cubic meters. It might be a bit more than that, a bit less than that. They're generally the volumes that are being dealt with in terms of beach nourishment in Victoria. If you look at other places around the world, so for example, in the Netherlands, where they do some enormous nourishments, this is the sand engine. It's on the order of 20 million cubic meters of sand. So the major changes to the coastline, when you do nourishments on that scale. All right, and then now the last of our processes and the time frame over which it operates is sea level rise. This operates over decades to centuries, so it's accelerating. What we expect here is that waves maintain the profile shape. So the profile ends up shifting up and onshore to conserve volume as sea level rises. And you do some simple geometry, the sort of thing, it might look complex when I add that on, but you could probably do this, a bit of high school geometry, is that these red areas have eroded, the blue areas have accreted, so accrete to build up. And we get this very simple relationship here, which is that the shoreline change is simply the amount of sea level rise divided by the slope in terms of the rise over the run. And that's known as the Bruin rule. Maybe if any of you are in this area, you might have heard of that, named after a guy that originally came up with the idea back in the 1950s. And more on this concept later. A couple of examples here where you see this technique or similar techniques, similar simple sort of empirical equations, geometric techniques being used in the Port Phillip Bay Coastal Hazard Assessment, and also in, you might be aware of the Victoria's Resilient Coast Guidelines. On to another myth. In regards to sea level rise, the myth here is that all beaches will disappear as sea level rises. And this myth you actually see perpetuated a little bit in the literature here and there, depending on how it's being done. In reality, whether or not a beach is going to maintain its width under sea level rise depends on accommodation space. So I was going to drop the jargon, but I think that one sort of helps you to understand it's the amount of space the beach has to move into. So beaches with natural dunes and room to move or accommodation space will naturally migrate up and onshore. This is the expectation. And beach width will be maintained. You can imagine that a sea level rise rose 100 metres over the last 6,000 to 10,000 years. Beaches didn't all disappear. They migrated in this fashion as sea level rose. And it's the beaches in front of cliffs and seawalls that are at risk as sea level rise accelerates. So narrow beaches in front of cliffs and seawalls are the ones that we need to address. And in particular, the problem that is so often faced in coastal management here in Victoria, that one there is, the shot I had is down at Apollo Bay. It's not in Port Phillip Bay, but face similar problems there, that when there's critical infrastructure built too close to the coast, the question becomes, do you put a seawall in to protect the infrastructure? Well, if you do, you might lose the beach. So now we'll take that quick introductory course on coastal change and coastal processes and look at that in the context of the Port Phillip Bay Coastal Hazard Assessment quite briefly. And in particular, it deals here with the erosion component of the Port Phillip Bay Coastal Hazard Assessment. I'm not dealing much with the inundation and groundwater components, if you're familiar with the report at all. So you might see here this image I've got from the technical summary on erosion. Now that equation might look familiar because it's quite similar to what we've introduced over previous slides. And the erosion hazard zone in the Port Phillip Bay Coastal Hazard Assessment is broken up into these three zones, the short-term and two long-term components, which we'll step through now. And so the first one here in green, matching this little green layer, notice it's quite thin. So short-term, as we said, deals with cross-shore sediment movement. In particular, we're thinking about storm demand. We call it storm erosion and recovery. Because the waves are quite small in Port Phillip Bay, at least away from the entrance. once you get into the majority of the bay. Erosion from storms, no matter which way you look at it, it's really quite small. And I think this is counter to a lot of people's expectations. So 1 to 5 meters, let's say, of erosion for big storms, and often a minor component. The long-term trend, which is a mix of the longshore and sources and sinks that we talked about, it's combined together by looking at aerial imagery and the vegetation line from old aerial imagery going all the way back to 1930, and then looking at the trend change in that vegetation line and extrapolating that forward. One thing that the method did do was remove large nourishments where they're identifiable from that trend. You can't pick up all the small nourishments. And the results here are highly location dependent. Some areas are retreating quite rapidly. Some areas are eroding quite rapidly. Most are smaller. But in terms of a range, it might be plus 100 meters to minus 100 meters. That's in terms of growth of the shoreline or erosion of the shoreline by 2100 is about the range that we're looking at. And in some areas, as I said, it's highly variable. But as in per this example here, the blue area is actually larger than there's more erosion due to that long-term trend than there is to the sea level rise component that we're going to talk about now. So the finding for the sea level rise component, the method used here were two simple equations similar to that one I showed earlier, the Bruin rule approach, but with a bit of a variation depending on the shape of the profile and that related to how big the waves are in that area. So rounding off to, say, for a metre of sea level rise, there was a scenario of 0.8 metres and a scenario of 1.1 metres sea level rise. The findings were that for areas with larger waves, by 2100, for a metre of sea level rise, you see on the order of, let's say, about 50 metres of erosion or recession. And areas with lower waves, a smaller number on the order of, say, 10 to 20 metres. And then for some areas, there's much larger uncertainty, say those dynamic spits that we looked at earlier, Swan Island and Altona. And in those areas, it's very difficult to predict, and there's large uncertainty applied to those areas and some other low-lying areas around the north of the bay as well. All right, I'm not going to spend too much more on the coastal hazard assessment directly. As I said, there's another workshop coming up tomorrow. And I should mention at the end that all of these are combined in a probabilistic method, which can make it hard to tease them apart in the final results, unfortunately. All right, all that's simple enough, I hope. Fairly straightforward, but it gets a little bit more complicated from here because we're going to talk about some of the issues around projecting coastal change out to 100 years in the future. And there certainly are some big issues here. The first one is, and this goes back to the previous talk, is that to make a prediction of shoreline change so that you're at the end of the line, it's a downstream impact. So you first have to deal with predicting, human behavior in terms of CO2 levels, and then you need to do all the climate modeling. So atmosphere temperature, wind, sea level rise comes out of that, wave climate. And then at that point, you can start thinking about coastal change. And then it's another step beyond that to do impacts and risk. So the result of that is that you have very large uncertainty before you even start. And as an example here, I'm showing this is work from Jin Liu, an ocean modeler, and other colleagues of his that was part of his PhD. This is projecting a wave climate out to 2100 and wave direction changes, and they might have very significant impacts, these wave climate directional changes, but they're often not incorporated into modelling. It's very difficult to do so. All right, that's issue one. Issue two is coastal change is highly variable at local scale. You need high resolution time space models in order to account for this. It might be very different 50 metres down the beach than what it is where you're standing. The good news is there are sophisticated models that can assess the impact of the storm quite effectively. The bad news is they really are only for the short term, maybe a few days to a few years ahead at most. It gets very hard to apply them beyond that. And it's not just for computational reasons and cost. Issue 3 is going to address another reason why. And issue 3 is that there are major coastal processes that are poorly understood. The physics of these processes aren't well incorporated into models, and small changes, if extrapolated out over many years, can give you a crazy result. Some of these processes are indicated in this cartoon on the right over here, looking down at the beach. This is from Mitch Harley and colleagues. 3 that I'll pick out that are particularly important because they're the most poorly understood are headland bypassing, exchange with estuaries, and this one here is really important and was the main topic of this paper, is transport from the deep subtidal onshore when you occasionally get hit with really extreme storms and you're way out past where the waves are breaking, but those extreme storms actually bring sand onshore. And the finding of this paper was that it could offset up to 20 years of climate change and sea level rise based on a workaround here is you can bundle up all these processes that you can't really identify accurately or precisely, and you can extrapolate historical trends. I often do this. It's what's done in the coastal hazard assessment, but trends often change, especially if you're talking about over, say, 100 years into the future. So it's a big problem. Issue 4, which is a major one, is we don't really know how coasts will respond to sea level rise. So you saw that simple geometric approach I showed before, the Bruin rule, or there's similar approaches, but they're all similar. It's used in most coastal hazard assessments. And this approach has been widely criticised by scientists and engineers for decades, but there's no real viable alternative at this stage. And to address this, I'll introduce another myth. So the myth is most of the coastal erosion we are seeing now is related to or is caused by sea level rise. That's not correct. The reality is it's very difficult to find sea level rise related erosion impacts. It's not impossible. A few people trying to do it, but certainly at a regional or global scale, the signal is still smaller than noise because of those other processes that I talked about, the cross-shore, your longshore, and the sources and sinks. So let's say we've had 20 centimetres sea level rise over the past 50 years, a bit more than that. The Bruin rule predicts we should get about 5 to 10 metres of erosion from that, but this is not apparent from observations, say from the satellite observations. And again, the issue here is the resolution of your observations versus the signal versus the noise. And also potentially there's a lag here, or there's other factors like we're not accounting for that onshore transport process. And, maybe some good news from that is maybe the erosion that we're projecting, say, with these types of approaches might be more conservative than we turn out to see, but we really don't know that yet. The erosion that we see now, it's not sea level rise. It's generally those other processes, the short-term storm erosion overlaid on some of the negative sediment budgets, the long-term trends, so from onshore drift. This paper I've shown over here, it deals, from Andy Short, it's great, deals with a lot of these topics, ocean and coastal management. Even if you just read the abstract or look at a few the pictures, this clarifies a lot of my thinking on this. It's a couple of years old now, and it deals with a lot of these topics that I'm talking about. So the outcome of all of that is that long-term coastal erosion hazard projections are typically, and I would say unavoidably, highly uncertain, and they have to be highly simplified for the reasons that we talked about. So some processes are not accounted for. You have to introduce simple empirical equations. And another one is erosion and inundation hazards are treated independently, but those hazards are definitely dependent on one another. All right, just a couple more slides here. I'm now going to talk about some alternative approaches we've been seeing coming through in the last few years, mostly still in research, but it's starting to get through to into consultancies and therefore accessible to governments and whoever land managers that are doing coastal hazards assessments. And I call these hybrid models because you're normally cobbling together a number of different models, one for the short-term storms, one for the longer-term alongshore transport, the longshore drift, and another one for the sea level rise. It doesn't solve all the problems that we've talked about, but it attempts to deal with some of them. You can ask different questions with this approach. Say, how long will the beach last? How much nourishment might be needed to maintain the beach to 2100? Or what will be the impact of a storm in 2100, combining those erosion and inundation hazards? And then you could also look at what are the impacts of a change in wave direction using this approach, as we also talked about earlier. So you're combining the standard sort of hazard management and assessment that you see now with more looking at beach management as well, like this paper we see over here from Nature last year. One of the best examples of one of these types of models that we're seeing now applied to one beach, that you could save a lot of money by avoiding floods by nourishing the beach. It says here by 2050, flood reduction and recreational benefits cost more than 150 times the cost of doing the nourishment. All right, following on from that idea of nourishment, can at-risk beaches be maintained in Port Phillip Bay? I'd say that we're using a simple version of one of these hybrid models in Port Phillip Bay that the project's done, and we'd like to now talk about how other government organisations and land managers do this type of modelling. The myth we've got here is beach nourishment is a temporary solution. The reality is, well, it might be, depending on how much sand and money you've got, but it's a matter of calculated sediment budget, dollars budget, and then determining how much sand you need and over what time frame you're going to need it. So the studies we've done with VCMP, there is likely sufficient sand in Port Phillip Bay, most beaches, to get to nourish to 2100 if that's what you chose to do. There's one study here that recently was completed for Sandringham again, is that an additional 10 to 20,000 cubic metres per 1 kilometre of beach every 10 years or so might be enough to offset 0.8 metres of sea level rise to 2100. So it's an interesting way to approach the problem, and I think quite appealing to land managers. All right, I'm going to finish up just in summary, saying, taking my perspective, how do you interpret and apply this to the results of the Port Phillip Bay Coastal Hazard Assessment? I think, unfortunately, you need to get comfortable with the unavoidable reality that although planning and management require certainty, science, in particular in this area, deals with uncertainty. It's very large. So you need to make certain decisions, like drawing a planning line on a map, but understand that it will be revised over time. If you understand that context of how much there uncertainty there is to the science and projecting a shoreline 100 years ahead. I will, in bold here, say that Port Phillip Bay Coastal Hazard Assessment is the best available data, and we're strongly encouraging from DCA to be applied as widely as possible. Now, you might need to do additional local studies, and the adaptation pathways approach that's promoted through Victoria's Resilient Coast, I think, is an excellent way to deal with this idea of large uncertainty, that you've got options and trigger points that even if things turn out to be not as expected, you can take a different pathway and adapt. All right, that's all from me. And just a reminder, there is another final workshop on tomorrow.
Thanks very much, Jack. Super enlightening, and it's certainly, I think, further discussion with regards to and how this ties into life-saving services around the bay is going to be sort of the discussion for the future. I'm going to pass over to Hayley just to cover off questions for James or Jack.
Thank you, Paul. So yeah, for those of you that don't know me, my name is Hayley Jarvis, and I'm the Executive Officer at the Association of Bayside Municipalities, and we're a proud delivery partner of the Nature of Change series. So tonight, as Paul said, I've been tasked with facilitating the Q&A. So thank you for those questions that have come in. We'll delve into some of them now. Starting off, we've got a question from Sue. I think this one's for you, Jack, but Sue said, Eric Bird spoke of sand moving from one end of the beach to the other. What effect has the dredging of the bay had on this?
So sand going from one end of the beach to the other, that was, I've read some of the Eric Bird stuff, and that gives a qualitative interpretation of that example I showed for Sandringham, the work that Dave Kennedy and his group have done, where I think I said at the end that you can see up to 30 metres of change at the ends of that beach just on a seasonal scale. So that's that part of the question. And but then relating it to dredging, well, that process directly and in that area of the bay, it's not going to have an impact. But I'm quite aware of the various work. I assume it's referring to the channel dredging and things happening at Portsea and that sort of thing. I'm aware of some of the modelling and the various phases of modelling work that's been done around that, and some of it's quite compelling, I would say. So the impacts on wave height at the shoreline in some areas around the bay based on dredging of the channel could expand on that, because it does also larger waves. So let's just say, let's just hypothesize for a second, but if you were to dredge a channel and it was to cause larger waves impacting the shoreline at an angle at a certain point, it would move more sand from that area and erode that area, and that sand would end up somewhere else further down the line. And that may be something that has occurred in Port Phillip Bay. But it's not quite as direct as I would like to be with that answer.
Tough question off the bat there for you. We'll move to the next one. So the next one's from Maddie, and it's also to you again, Jack. With an increase in magnitude and frequency of storm events, do we expect more of that sediment to be trapped offshore, or do you think there is still ability for the beach to recover?
Yeah, to some degree, but remembering that storm component is quite small. So I suspect it won't be a major component of long-term shoreline change. But there may be some degree of that happening, that that you end up with a beach state where there's more sand more of the time that's in the subtidal bar than on the beach. But I don't think that's going to be a huge effect.
Very good. And just a reminder, if you do have any questions, just pop them in that Q&A box down the bottom. We've got a question from Marilyn. I'd like to know whether the deepening of the rip several years ago at the entrance of Port Phillip Bay to accommodate larger cargo ships has had an effect on beaches in Port Phillip Bay.
Oh, that was the answer to my previous question that I was sort of a bit vague about. Did you want me to do that one again? Because that was effectively that's what I thought was the previous question. That's what I answered with. And I just apologise for being a bit vague. I don't know if anyone knows the history. I don't know why.
Right, that's fine. So we did answer the previous one as well, didn't we?
Yeah. So I said, I'll try and say it concisely. In a little bit like in the hypothetical, that if you were to deepen a channel and it caused larger waves to impact a particular part of the shoreline, then it would, and it was at an angle to the shoreline, it would likely drive sand away from that area, cause that area to erode, and you would then see somewhere down the line that sediment deposited. And if you follow this thought through, you might see other areas down drift of the area we're talking about that have accreted rapidly over that time frame. So it's certainly possible. Very
good. We'll come to the end of the questions, but one that I have, you mentioned the Port Phillip Bay Coastal Hazard Assessment workshops that are taking place. I realise there's one more. How do our participants join? Is there a link or something that I can? Yeah, I might forward it to you. I hope that it's just open, but I'm not certain. But I know that all those invited to the previous ones, there's lots of different government organisations and land managers, and that's generally the crowd. So I'll forward that one on to you now, and then just forward it out to everyone and see if it works. And whilst we've been talking, we've got another question's come in from Sue. Sue asks, the bluestone wall at Blackrock is regularly damaged. What is causing this? Specifics there. Is that
is there, Sue, could you give me the, exactly where are we talking about? Is Black Rocks,
Half Moon Bay.
yeah. Ah, of course, yeah. Yes, yeah. I was down there not so long ago looking at that. There's certainly it's one of these things, there's highly variable localized effects, and then you get issues with, when you're putting infrastructure sort of, in some of these zones that can be quite dynamic. And I would, my first, without knowing the detail of like the individual seawall, but having been there, it may be undermined by those longshore processes, moving sand away from in front of the wall to potentially further towards the north, up towards Sandringham. And if the base of the wall is exposed, then if you do get larger waves coming in at some point, then you can see damage occurring. So that's one possibility.
I'm going to go over to you now, James, if I can. We've got a question from Greg. If the world reduced its production of CO2 substantially very quickly, how long would it take to turn around its effect on climate change?
I thought I'd got away with no questions then. Thanks, Greg. No, I'm kidding. Oh, gosh. Well, it's going to be very hard for us to substantially reduce CO2 for the foreseeable future, because countries are already trying to make those changes, and they're not being reflected in the CO2 atmospheric concentrations. It would probably take hundreds. We're locked in for decades to possibly hundreds of years of what is occurring at the moment, before we start seeing it decrease. I mean, I know that the IPCC were expecting it by 2040, 2050 for us to start decreasing the amount of CO2 in the atmosphere. I think those projections are now out completely, because we're already above what the Paris Accord was suggesting CO2 concentrations would need to be in order to keep us to 1.5 degrees Celsius maximum warming. So when you look at the amount of heat now which is in the oceans, which has been taken up by the oceans, take up a lot of the heat which is in the earth at the moment, plus the CO2 concentrations in the oceans, which have been increasing quite substantially. The pH of seawater has actually decreased from 8.2 to 8.1 pH, which doesn't sound like a lot, but it really is having an effect on our marine ecosystems. So I think we're kind of locked in at the moment. Even if we started cutting drastically now, it would still take decades for that to be reflected in the atmosphere on Earth. By the way, cute dog.
Yeah, thank you.
Mine's over in the corner, demanding a walk.
You must know it's almost time to wrap up. But just a comment to James. Marilyn's just said, thank you for the great greenhouse effect revision. My 1970s lectures needed a bit of updating. So that's very good. And we've just got, I might kind of combine them. I think, Jack, I'm sorry to bring you back in. I've just got a couple here. Alan's just said, sorry to ask about Portsea again, but with the work there to address erosion, so sandbags and rock work, is that an adequate response?
There's a range of proposed options. I don't know how it becomes a bit subjective, like in terms of what's adequate or what's a good solution, because it's not necessarily a question down to the science. It gets to more policy and who are you trying to please and what are you trying to achieve. So I don't know, you could put one of the proposals I've seen, you could put a groin in further towards the east, and then that would allow you to trap sand that was being moved away from that area. But then there were some concerns over impacts on seagrass and things beyond in that region towards the headland towards the east there. As to what, just maybe that question of whether it's adequate, I don't think you want to have like a temporary solution like those bags there for too long. So you got to kind of make a call. Like one decision could be, we're going to have a hard seawall but no beach there. Another option could be, we're going to have a serious nourishment program and try and maintain a beach there. It's going to be hard with the amount of erosion that occurs. And then who's going to pay for that? And then or you could have a combination, my first suggestion, of some sort of structure, say a groin, something else, and then combine that with a nourishment strategy. And then each of those has to be weighed up as to who they upset, how much they cost, and potential ecological impacts as well.
Okay, I think the questions are really coming in now. I think we've got time for just a couple more. One from Peter, just the effects of more and larger cargo ships on shoreline.
Well, that in terms of like wake effects, look, there could be. It's not something I'm really that familiar with. It's not knowing, how close some of those ships are getting to shore. But maybe if there were some low, muddy shorelines, like more off towards the northwest of the bay, and they were impacted by wakes, I could see that being an issue for erosion of those banks. But I'm really not familiar with that area.
We can't, it's hard to, we're really putting you on the spot here. It's a bit of a
that's fine. There's a lot of Portuguese questions, but I didn't focus on that at all.
Well, we've got one more each. So James, we'll go to you. Marnie's just asked, is the methane, etc., from massive numbers of African ungulates, I hope I've said that right, counted in the global warming factors?
Ungulates. Now, I must admit, I had no idea what that word meant, and I've just quickly, literally Wikipedia'd it. So thank you, Wikipedia. So I now know we're talking about African-hooved mammals, I think it said, but don't always trust Wikipedia. I have no idea. What I will say is that it's been quite interesting. The last, sea level rise predictions. With each IPCC report that comes out, changes because we've got new data, new methodologies, etc., and they've been increasing. And I found what was quite interesting is the IPCC 5, I think it was, had the average sea level would increase by 0.8 or 0.76 meters by 2100. IPCC 6 came up with 0.84 meters in sea level rise. But I know that the modelling, as I understand it, did not include some important processes which are now being included. And I'm pretty sure that the melting of the permafrost was not included in previous sea level rise work. I could be wrong on that, but I'm pretty sure that's correct. And because of that, that's now being incorporated. And so we're looking at sea level rises of more than 1 meter. Again, it doesn't sound a lot, but as you saw from Jack's work that he presented, this, it could well have a significant effect in some areas. I would also add that methane emissions, methane is, I think it's a much more potent greenhouse gas than carbon dioxide. It's got a longer residency time in the atmosphere, and it also has a higher heating potential as well. So methane's a pretty nasty greenhouse gas. I know we focus on CO2, but methane's another big one.
You've done well, given that you just Wikipedia'd that. That was very good. And the final one, which I think looks like it's for you, Jack. Dinah's just asked, there's no such thing as a stupid question here, but she's saying, should we look at removing some of the man-made structures that may have negatively impacted natural sand movement in the bay? And an example she's given here is that she can't look at the accretion around Swan Island and the front beach at Queenscliff without wondering whether the cut has had an impact.
Yeah, it's tricky. So the initial question there was, is it possible to remove any of these structures? And let's say those groins at Sandringham that I used many examples of, just done the modelling work there, they have been played around with in the past, in lengthened, shortened, another one put in. When I see, say, as Indika, sort of the coastal expert into advise on some of these projects with the project managers and engineers, and it's very difficult to see a scenario where you can remove some of the structures because it's expensive, it causes other impacts, and that the reality of that makes it quite difficult. I've seen sometimes. It's not my area. I'm sort of just in there sometimes advising on this. As to like the initial idea, yes, often it would be beneficial in terms of what you're doing to sediment fluxes and transport. That it was probably a mistake to put it in initially. In some instances, it'd be great if you could remove it. Whether you can actually do that in reality is, as I've said, it seems quite hard. And for it was the example of down at Queenscliff and Swan Island down there. I'd imagine, look, I don't know the details of that again, but I'd imagine that there's issues around structures around that harbour that mean that it would be very difficult to just say, all right, we're going to revert to a natural, more the initial environment here and take out the structures. It's just, I don't know the details, but assuming that. I would say that it just occurred to me, there was talk, I don't know how far it's progressed, but some of the, what they call the coastal, near Avalon, some of the ponds that were around there, I did see talk of potentially making them tidal again. And so, that type of idea is a possibility that you can engineer an environment back to a more natural state. And, there's a few examples of it, but just revert to that initial point that I think it's quite hard and quite expensive, and you run into other problems like with that side. I think it's a Ramsar site or something as well.
Very good. Thank you. Thank you both for your answers, and thanks to our audience for the questions that were raised. I'm going to hand over to Shannon now to wrap up. I hope I haven't gone too far over time, Shannon.
Thanks, Hayley, and thanks everyone for sticking with us till the end. Please join us in sending a huge thanks to Jack and James. Just, super knowledgeable presentations. Woo! Learnt a lot myself, and I know that everyone else in the audience, I trust, did as well. So thank you again, and for everyone watching at home, we have 2 more webinars left over the next coming months, and we'll be in touch on the email list with some more details when we have organised them and we have some more dates for you. But we will send around the recording in the coming days as well. So thanks again, everyone, and enjoy your evening.